Welcome to Night Lesson. Relax and learn along the way. From the Big Bang to today, the history of the universe. A soothing journey through 13.8 billion years. A night lesson for falling asleep. Welcome to this night lesson on the history of our universe. Over the next few hours, we will journey together through unimaginable expanses of time. From the first fractions of a second after the Big Bang to the distant future, trillions of years from now. Please, make yourself comfortable. Close your eyes, if you wish. Let the gigantic spans of time, the infinite expanses, and the silent majesty of the cosmos guide you into sleep. The story of the universe is a story of patience. Nothing happens hastily in the cosmos. Stars take millions of years to form. Galaxies take billions of years to find their shape. And as we wander through this history, we will discover that we, you and I, are made from the very atoms of this cosmic story. Let us begin at the beginning. 13.8 billion years ago, in the hottest, densest moment the universe has ever known. There is no moment in the history of the universe more fascinating than the beginning. 13.8 billion years ago, a number so vast it almost seems meaningless, everything began. But what does it mean for everything to begin? It did not begin in a place. It did not begin at a time in the usual sense. The Big Bang was not an event in space, but the beginning of space itself, the beginning of time itself. In the first 10 to the power of minus 43 seconds, that is a zero, followed by a decimal point, followed by 42 zeros, and then a 1. The universe existed in a state we can barely describe. Physicists call this phase the Planck era. In this unimaginably brief period, all four fundamental forces of nature were unified: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They were not yet separate. The universe was smaller than an atom, hotter than we can possibly imagine, about 10 to the power of 32 degrees Celsius. Then, after this Planck time, the universe began to expand. And it did not expand slowly. It virtually exploded in size. We call this phase cosmic inflation. In a fraction of a second, between 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the power of 26. To visualize this, imagine something as small as an atomic nucleus suddenly swelling to the size of a galaxy. And all of this in less time than it takes a beam of light to cross the width of a proton. During this inflation, the universe cooled rapidly. The unified force split apart. First, gravity separated. Then, shortly after, the other forces separated. The universe now had its four fundamental forces, which govern it to this day. After about 10 to the power of minus 12 seconds, 1/trillionth of a second, the universe had cooled to about 1 trillion degrees Celsius. Still unimaginably hot, but cool enough for quarks to exist, the fundamental building blocks of matter. These quarks swam in a hot soup of energy and particles. The universe was a seething, chaotic mass of energy and emerging matter. Photons, particles of light, were constantly being absorbed and re-emitted. The universe was opaque, a dense fog of energy. After 1 microsecond, 10 to the power of minus 6 seconds, the universe had cooled further to about 10 trillion degrees. Now, quarks could combine to form protons and neutrons. The building blocks of atomic nuclei began to exist. Let these numbers wash over you. All of this, the separation of forces, the emergence of matter, the formation of protons and neutrons, happened in the first microsecond. In the time it takes to blink an eye, trillions of such cycles had already passed, and the universe continued to expand. Every second, it grew larger, cooler, emptier. After this chaotic first second, the universe entered a phase that was somewhat calmer, at least on a cosmic scale. The universe was now about 1 second old. The temperature had dropped to about 10 billion degrees. That is still hotter than the center of the sun, about 1,000 times hotter. But it was cool enough for something decisive to happen. Neutrons and protons could now exist stably without being immediately destroyed again. In the next few minutes, something wonderful would occur. Something that, billions of years later, would form the basis for stars, planets, and life. When the universe was about 3 minutes old, 180 seconds after the Big Bang, primordial nucleosynthesis began. The first atomic nuclei came into being. Protons and neutrons started to combine. One proton and one neutron formed deuterium, heavy hydrogen. Two protons and two neutrons formed helium-4. Smaller amounts of helium, 3, lithium, 7, and tiny traces of other light elements also formed. This process lasted only a few minutes. By the time the universe was about 20 minutes old, it had become too cool for further nuclear fusion. The temperature had fallen to about 100 million degrees, too cold to fuse atomic nuclei. The result of these first 20 minutes was remarkable. The universe now consisted of about 75% hydrogen and 25% helium by mass. In addition, there were tiny amounts of deuterium, helium-3, and lithium, together less than 1%. These ratios, 3/4 hydrogen, 1/4 helium, are preserved in the universe to this day. When we look at the most distant galaxies, we see this ratio everywhere. It is the chemical legacy of the first 20 minutes of the universe. But the atomic nuclei did not yet have any electrons. The universe was still too hot. Electrons could not remain bound to nuclei. They were immediately knocked away again by the intense radiation. The universe consisted of a plasma, free atomic nuclei, and free electrons, permeated by intense radiation. Light could not travel freely. It was constantly scattered, absorbed, and re-emitted by the free electrons. The universe was opaque, like a dense fog, and so it would remain for a very, very long time. After the first exciting minutes, the universe entered a phase that would last for hundreds of thousands of years. A phase of waiting. The universe continued to expand. It continued to cool. But, seemingly, nothing dramatic was happening. No new structures were forming. No stars were shining. No galaxies were taking shape. The universe was a hot, dense plasma of atomic nuclei, electrons, and photons, slowly, patiently cooling. The temperature dropped from millions of degrees to hundreds of thousands of degrees, then to tens of thousands of degrees. When the universe was about 380,000 years old, it reached a critical temperature, about 3,000 degrees Celsius. That is about as hot as the surface of a cool star. At this temperature, something fundamental happened. The electrons could finally be captured by the atomic nuclei. Hydrogen nuclei, single protons, captured electrons and became neutral hydrogen atoms. Helium nuclei captured 2 electrons and became neutral helium atoms. This moment is called recombination. Although it was actually the first combination, recombination is just the historical term. Within a few tens of thousands of years, the entire universe became neutral. And that had a dramatic consequence. The universe became transparent. Suddenly, on a cosmic scale, photons could travel freely. They were no longer constantly scattered by free electrons. The light that existed during recombination could move freely through space. This light travels through the universe to this day. It has been stretched and cooled by the expansion of the universe. Today, it reaches us as microwave radiation, the cosmic microwave background. We can measure it with special telescopes. It comes from all directions, a quiet reminder of that moment 13.8 billion years ago when the universe became transparent. But even though the universe became transparent, it remained dark. For there were no sources of light, no stars, no luminous objects, only neutral hydrogen and helium atoms, drifting silently through space. The Dark Age had begun. It would last for over 100 million years. During this time, The universe continued to expand. The temperature continued to fall. Matter grew thinner and thinner. But beneath the surface of this apparent stillness, something began to happen. Dark matter, a mysterious form of matter that emits no light and interacts only through its gravity, began to form structures. It clumped together, and in these clumps, normal matter, the hydrogen and helium, began to gather. Slowly, over millions of years, these gas clouds condensed. Gravity pulled them together. They grew denser and denser until finally, after more than 100 million years of darkness, the first lights in the universe began to shine. Around 150 to 400 million years after the Big Bang, something beautiful happened. The first stars were born. These first stars were not like our sun. They were gigantic. Some had 100 times the mass of our sun, some even more. They were born from pure hydrogen and helium, the only elements that existed at the time. Imagine a vast cloud of hydrogen gas, slowly collapsing under its own gravity. The cloud is light years across, millions of times larger than our solar system. But it grows denser. In the center, the pressure rises. The temperature rises. After millions of years of contraction, the center reaches a critical temperature, about 10 million degrees. At this temperature, nuclear fusion begins. Hydrogen nuclei fuse into helium. And in doing so, energy is released, a tremendous amount of energy. The first star ignites. Suddenly, it radiates light. Intense, brilliant light. It penetrates the surrounding gas clouds. It ionizes the hydrogen, turning it back into protons and electrons. A bubble of ionized gas expands around the star. These first stars are called population 3 stars. We have never seen one directly. They are too far away, too long ago. But we can calculate what they must have been like. And the calculations show they were bright, incredibly bright. A typical population 3 star was perhaps 1 million times brighter than our sun. Its surface was much hotter, 50,000 degrees or more, compared to the 5,500 degrees of the sun's surface. It shone with an intense blue-white light. But these gigantic stars paid a price for their brilliance. They did not live long. A star like our sun can exist for 10 billion years. These early giants lived for only a few million years, some for only a few 100,000 years. They burned through their fuel at a furious pace. In the core, hydrogen fused into helium, then helium into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, a whole cascade of fusion processes. In the end, at the star's core, iron formed. But iron cannot fuse and release energy. The fusion stops. And then, suddenly, the star collapses. In fractions of a second, the core implodes. A shockwave races outward. The star explodes in a tremendous supernova. These explosions were so bright that they illuminated entire regions of the universe. And they had a crucial significance. They hurled all the heavy elements that had formed inside the star out into space. Carbon, oxygen, nitrogen, silicon, iron, all the elements that would later be essential for planets and life, were distributed into the universe by these first supernovae. The first stars died, but their death enriched the universe. From their remnants, new stars would arise. Stars with planets. Stars with the possibility of life. While the first stars shone and died, larger structures were forming. The gravity of dark matter had created filaments, vast, thread-like structures stretching through the universe. At the intersections of these filaments, matter collected. About 400 to 600 million years after the Big Bang, the first galaxies emerged. These early galaxies were small, much smaller than our Milky Way is today. They might have contained a few million or a few tens of millions of stars. The Milky Way today has over 200 billion stars. But these small galaxies were seeds. They collided with one another. They merged. Larger galaxies were born from the union of many smaller ones. The universe was now 1 billion years old. Everywhere, stars were forming. Everywhere, Galaxies were shining. The Dark Age was over. The universe became a sea of light. In the centers of the largest galaxies, something special was happening. Supermassive black holes were forming. These black holes had millions or billions of times the mass of our Sun. How exactly they formed is still not fully understood. Perhaps they grew from the remnants of the first stars. Perhaps giant gas clouds collapsed directly into black holes. These black holes devoured matter. And when matter falls into a black hole, it becomes extremely hot. It shines brightly before it crosses the event horizon. The region around these black holes became the brightest objects in the universe, quasars. A quasar could outshine an entire galaxy. Some quasars were so bright that we can still see them today, even though their light has traveled over 13 billion years to reach us. The universe was evolving. Galaxies grew. Stars were born and died. With each generation of stars, the universe became richer in heavy elements. The first stars consisted only of hydrogen and helium. The next generation contained tiny traces of heavier elements. Then more and more. After about 2 billion years, the universe had produced enough heavy elements that planets like Earth became possible. Rocky planets. Planets with iron cores, with silicate rock, with oceans of water. When the universe was 2 to 3 billion years old, a phase began that would last for a long time, the era of galaxy formation and evolution. Galaxies formed groups. Groups formed clusters. Clusters connected into superclusters. The universe developed a large-scale structure, a cosmic web of filaments and voids. If you look at the universe on a grand scale, not individual stars or galaxies, but the distribution of galaxies over billions of light years, you see this web. Long filaments of galaxies, punctuated by vast empty spaces, the voids. This structure was not random. It was a direct consequence of the tiny density fluctuations that existed shortly after the Big Bang. Regions that were minimally denser attracted more matter. They grew even denser. Regions that were minimally less dense lost matter. They became the voids. Gravity shaped the universe over billions of years. Within the galaxies, an endless cycle played out. Stars formed from large molecular clouds. Massive stars lived briefly and exploded as supernovae. Their remnants enriched the molecular clouds with heavy elements. From these enriched clouds, new stars were born, and these new stars sometimes had planets. It was a cosmic alchemy. The heavy elements we know today, carbon, nitrogen, oxygen, iron, gold, uranium, they were all forged in stars or created during supernovae or neutron star collisions. Carbon, the basis of life, is formed in red giant stars through the so-called triple alpha process. Oxygen, the second most abundant element in your body, is created in massive stars shortly before their end. Iron, which flows in your blood, is formed in the final moments before a supernova. The heaviest elements, gold, platinum, uranium, are forged in the most violent events in the universe, when two neutron stars collide, or when a black hole devours a neutron star. The universe was a factory, a patient factory that, over billions of years, manufactured the elements that would later make life possible. Around 9 billion years after the Big Bang, the universe was now mature, full of heavy elements. Something happened in an inconspicuous spiral arm of an average galaxy. That galaxy was the Milky Way. And in a vast molecular cloud in one of its outer arms, a densification began. Perhaps the cloud was struck by the shock wave of a nearby supernova. Perhaps it was simply gradual gravitation. The cloud began to collapse. In the center of this cloud, matter condensed. A protostar formed, a hot, dense collection of gas not yet shining through nuclear fusion. Around this protostar, a disk of gas and dust rotated. In this disk, dust grains began to stick together. Tiny grains became pebbles, pebbles to boulders, boulders to asteroids. After a few million years, planetary embryos had formed, bodies the size of the Moon or Mars. About 4.6 billion years ago, 4,600 million years ago, nuclear fusion ignited in the center. Our star, the Sun, was born. The fierce solar wind swept light gases from the inner solar system. That is why the inner planets, Mercury, Venus, Earth, Mars, became rocky and relatively small. Farther out, where it was cooler, giant gas and ice planets could form. Jupiter, Saturn, Uranus, Neptune. Earth formed from the collision and merging of these planetary embryos. About 4.5 billion years ago, a Mars-sized body collided with the young Earth. The debris from this collision formed the Moon. The early Earth was hot. Its surface was molten, but slowly, over millions of years, it cooled. A crust formed. Volcanoes spewed out gases that formed an atmosphere, mainly carbon dioxide, nitrogen, and water vapor. Comets and asteroids bombarded the young Earth. Some of these celestial bodies brought water. Gradually, about 4 billion years ago, the surface cooled enough for water to remain liquid. The first oceans formed. And in these oceans, in warm shallow bays or at hot deep-sea vents, something extraordinary began about 3.8 billion years ago. The first self-replicating molecules formed. Life arose on Earth. At first, it was simple single-celled organisms. Then, about 2.5 billion years ago, some bacteria developed the ability for photosynthesis. They began to use sunlight and, in the process, produced oxygen. Slowly, oxygen accumulated in the atmosphere. It took almost a billion years, but finally, about 2 billion years ago, the atmosphere became oxygen-rich. This enabled more complex life. Cells with nuclei emerged. Multicellular organisms developed. About 540 million years ago, the diversity of life exploded, the Cambrian explosion. Life conquered the continents. Plants grew. Animals evolved. Dinosaurs reigned for 165 million years before an asteroid impact wiped them out 66 million years ago. And in the void left by the dinosaurs, mammals spread. Primates evolved. And about 300,000 years ago, a blink of an eye in cosmic history, on an average planet around an average star in an average galaxy, a species arose that began to think about itself. Homo sapiens. Humanity. You and I. We are made of atoms forged in stars. The carbon in our cells, the oxygen in our lungs, the iron in our blood. All of it was created in stars billions of years ago. We are stardust that has begun to ponder its own origin. While life was evolving on Earth, the universe continued on its path. Galaxies continued to evolve. Stars were born and died. The cosmic web of filaments and voids became more pronounced. But something strange was happening that no one noticed for a long time. In the 20th century, humans began to systematically measure the universe. They measured the distances to galaxies. They measured how fast galaxies are moving away from us. A scientist named Edwin Hubble discovered in the 1920s, the universe is expanding. All galaxies are moving away from each other. The farther away a galaxy is, the faster it recedes. This discovery led to the Big Bang theory. If the universe is expanding today, it must have been smaller in the past. Much smaller. Physicists were able to calculate backwards and found the universe must have begun about 13.8 billion years ago in an extremely hot, dense state. But there was a question. Would the expansion continue forever? Or would gravity eventually stop it and cause the universe to contract again? To answer this question, astronomers in the 1990s began to observe distant supernovae. These supernovae could serve as standard candles, objects of known brightness. By measuring how bright they appear, one can calculate how far away they are. The measurements were supposed to show how much the expansion of the universe was slowing down. But in 1998, a shock came. The expansion was not slowing down. It was accelerating. The universe was expanding faster and faster. And that made no sense. Gravity should slow the expansion, not accelerate it. The explanation physicists found was astonishing. There must be a form of energy that permeates space itself, an energy that does not attract like gravity, but repels, an energy that drives the universe apart. They called it dark energy. And when they calculated how much of it must exist to explain the observed acceleration, they found something amazing. About 68% of the total energy of the universe consists of this dark energy. Another 27% is dark matter, the invisible matter that only interacts through gravity. And only about 5% is normal matter, the matter of which stars, planets, and we are made. We live in a universe that we mostly do not understand. 95% of the universe is made of dark matter and dark energy, things we have never directly detected, but we can see their effects. Dark matter holds galaxies together. Dark energy drives them apart. Today, 13.8 billion years after the Big Bang, the universe is a vast, expanding space full of galaxies. There are at least 200 billion galaxies in the observable universe. Some estimates even suggest 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The observable universe, the part we can theoretically see, has a diameter of about 93 billion light-years. This is larger than 13.8 billion light-years because space itself is expanding. The light from distant objects took 13.8 billion years to reach us, but those objects are now much farther away. But the observable universe is probably only a small part of the entire universe. We cannot see further because the light from more distant regions has not yet reached us. The entire universe could be infinitely large. At the center of most large galaxies sits a supermassive black hole. In our Milky Way, it is Sagittarius A*, with about 4 million solar masses. In other galaxies, the central black holes are even more massive. Some have billions of solar masses. New stars are forming throughout the universe. In our Milky Way, about 1 to 2 new stars are born each year. In some galaxies, the starburst galaxies, it's hundreds per year. But the rate of star formation is declining. 10 billion years ago, more stars were forming than today. The large gas clouds from which stars are born are slowly being used up. The universe is middle-aged. It has left its wild youth behind when new stars were exploding everywhere. It has entered a quieter phase, but it will not always stay this way. Let us look into the future. Not the near future, not in centuries or millennia, but into the distant cosmic future. Into time spans so long that they exceed our understanding. In about 4 billion years, our sun will become brighter. It has already lived half its life. In 4 billion years, it will be so bright and hot that Earth's oceans will evaporate. Earth will become uninhabitable. In about 5 billion years, the sun will swell into a red giant. It will engulf Mercury, perhaps Venus too, maybe even Earth, although Earth might move to a slightly wider orbit as the sun loses mass. In about 7 to 8 billion years, the sun will shed its outer layers. It will become a planetary nebula, a colorful, glowing shell of gas. At the center will remain a white dwarf, a hot, dense core about the size of Earth, which will slowly cool over trillions of years. But that is just our local story. What happens to the universe as a whole? In about 4 billion years, our Milky Way will collide with the Andromeda Galaxy. The two galaxies will slowly approach each other, drawn by their mutual gravity. They will merge into one another, their stars swirling around each other. The galaxies will fuse into a larger elliptical galaxy. Do not worry, stars are so far apart that actual collisions will be extremely rare. But the shape of both galaxies will change dramatically. In about 20 billion years, this merged galaxy will be alone in its local region. Dark energy will have pushed all other galaxies so far away that they are no longer visible. An observer in that distant future would see only one galaxy, their own, surrounded by empty darkness. They could never discover that there was a Big Bang, that the universe is expanding, that there are other galaxies. We live in a special time, a time when the universe is old enough to be interesting, but young enough that we can still recognize its history. In 100 billion years, most of the stars that exist today will have burned out. Star formation will almost come to a halt because most of the gas will be used up. In 1 trillion years, 1,000 billion years, almost no new stars will form. The universe will become darker. The era of stars will come to an end. Most stars will then be white dwarfs, burned out cores, slowly cooling. Some will have become neutron stars or black holes. But the story does not end in 1 trillion years. The universe will continue to exist, and we can continue to calculate, to extrapolate, ever further into the future. In 10 to the power of 14 years, 100 trillion years, white dwarfs will have cooled into black dwarfs, cold, dark spheres of crystallized carbon and oxygen. The universe will be almost completely dark, but stars still exist as dark remnants. Galaxies still exist as collections of these dead stars. In 10 to the power of 20 years, 100 quadrillion years, gravity will begin to eject stars from their galaxies. In random close encounters between stars, one star will sometimes gain enough energy to leave the galaxy. Slowly, over unimaginable spans of time, galaxies will fall apart. Most stars will drift in the empty space between galaxies. Some will fall into the central black holes of their former galaxies. In 10 to the power of 40 years, protons will decay, at least according to some theories. If this is true, all atoms in the universe would slowly disintegrate. The dead stars would dissolve into radiation. After 10 to the power of 40 years, the universe would consist mainly of black holes, photons, neutrinos, and electrons. And then, in the era of black holes, even these black holes would disappear. Stephen Hawking discovered that black holes are not completely black. They slowly emit radiation, called Hawking radiation. A black hole thereby loses mass very, very slowly. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole with 1 billion solar masses would take 10 to the power of 100 years. But eventually, they too would disappear. The last black hole would evaporate in a final flash of radiation. After that, nothing but radiation and elementary particles spread across an unimaginably vast space. The universe would enter a state that physicists call heat death. Everything would have the same temperature, just above absolute zero. No energy could flow from one place to another. No processes could take place anymore. The universe would be dark, cold, and empty. Forever. We have taken a journey through time. From the first fractions of a second after the Big Bang to the distant end, trillions upon trillions of years in the future. It is a story of unimaginable scale, of time periods we can barely grasp, of processes that stretch over billions of years. And in the midst of this vast history, we exist, tiny beings on a small planet around an average star in an ordinary galaxy. It is easy to feel insignificant. What are we compared to the size of the universe? What are our 70 or 80 years compared to 13.8 billion years? But perhaps we should see it differently. We are the universe thinking about itself. We are stardust that has developed consciousness. We are the cosmos awakened. Every atom in your body has a history that spans billions of years. The carbon in your cells was created in a red giant star that existed billions of years ago. The oxygen you breathe was forged in a massive star that exploded in a supernova. The iron in your blood was created in the final seconds before a star's death. You are literally made from the remnants of stars. And more than that, you are capable of understanding this history. You can think about the Big Bang. You can explore the laws of physics. You can look into distant galaxies and decipher their history. The universe has taken 13.8 billion years to create structures complex enough to think about themselves. And that is remarkable. Perhaps there are other intelligent beings somewhere out there. Perhaps we are not alone. The universe is so vast, with so many stars and planets, that it seems statistically probable. Or perhaps we are unique. Perhaps the emergence of life and consciousness is so unlikely that we are the only ones. We do not know. Not yet. But what we do know is this: we are here. Now, in this moment of cosmic history, the universe is young enough that stars still shine, old enough that heavy elements exist. We live in a golden age, the era of stars, of galaxies, of light. In the distant future, the universe will grow dark. But now it shines, and we have the privilege to witness it, to explore it, to understand it. We have reached the end of our journey. From the first fractions of a second after the Big Bang to the distant future when the last black hole evaporates. It has been a long journey, through unimaginable periods of time, through events of immense power and astonishing delicacy. The universe is a place of wonder, a place where hydrogen atoms, over billions of years, become human beings, where order arises from chaos, where infinite complexity emerges from simple laws. And you are a part of it. A tiny part, certainly, but a part that matters, a part that can think and feel and wonder. As you settle down now, as your thoughts slow and sleep embraces you, remember this: the atoms in your body are billions of years old. They were part of stars. They have traversed the universe. And now they are here, in you, in this moment. You are a miracle, an improbable, precious miracle. Sleep well. Dream of stars. Dream of galaxies. Dream of the long, silent history of the cosmos. Good night. To the stars. Yendi, night lesson, from the Big Bang to today. Total length, approximate 65 to 75 minutes reading time. Word count, approximate 9,200 words.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.